Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to calculate the moment of inertia of a mass distribution. So what we're looking at here is we've got some sort of long bar here. We're going to say it's got a mass m, total length L. And what we're going to try to calculate is the moment of inertia about an axis that goes through the end of the bar. Right. So in dealing with moment of inertia, usually what I do is I start by putting in some sort of coordinate system. I'm going to put a coordinate system right here. Right, there's my x, y, and then I'll go ahead and put a z-axis here. Right, and what we're looking to do is calculate the moment of inertia of this bar. And I'm going to imagine it rotating about the z-axis. Now it turns out the results will be the same if we're doing about the y-axis as well. Now moment of inertia, somehow how it's calculated. It's the sum of all the mr squareds on a body. But remember, if you think about that, what that means is basically, if I have some sort of object and I think about breaking it into a bunch of masses, right, and I have an axis of rotation, each of these masses has a moment of inertia about the axis, mr squared, mr squared, mr squared. And then the total moment of inertia is the vector sum of those. If I imagine these masses very, very small, like infinitely small, this would become a dm. And we'd be summing up an infinite number of them. So it kind of an equivalent way of writing this would be, I'll write it right here, di is equal to dm times r squared, and therefore I is equal to the integral of dmr squared. So the idea is we're going to break this up into a bunch of masses. They're going to be very, very small. In fact, we're going to call them dm small. Calculate the radius to each one and then add them all up. So we're going to imagine breaking this bar up into a bunch of little pieces. Right? Each piece here is going to have a length I'm going to call dx. It has an x coordinate here, and the x coordinate is the distance to the axis of rotation. So I can write this expression out. di, that's going to be the moment of inertia of this small mass about this axis, is equal to dm, the mass of that chunk, times x squared, where x is the distance from this chunk to this axis. Now, the dm, there's different ways to handle that. Remember that density is mass over volume. So if I knew a density and I had a volume, I could calculate an m. This could come up in some sort of moment of inertia calculations. I don't happen to need that right now though. So I would say, kind of keep this in mind for moment of inertia calculations. But here what I'm going to do is I'm going to calculate what's called the linear mass density here. I'm going to take the total mass, divide by the total length, and now I have a number with units of kilogram per meter. If I multiply by the length of my chunk here, my element, I would get the mass of that chunk. So this expression right here, m over L dx, would give me dm. That's going to give me the mass of this little chunk here. And then what I'll do is I'll just multiply by distance squared to give me the moment of inertia. So di, the moment of inertia of this mass about this chunk, can be written m over L dx, there's my dm, times x squared. Okay. Therefore, the total moment of inertia we would get by integrating both sides. We're going to have the integral of m over L, and I'm going to go ahead and write this in a more aesthetically pleasing way, I guess. And then we just got to decide the limits of the integral. Now the limits of the integral are going to depend on where you put your coordinate system. In my example, right, the furthest to the left this chunk can be is right here, so that's going to start at 0. The furthest to the right is right here, that's going to equal L. I'm going to go ahead and integrate that, so we're going to have, remember, anything constant can come out in front, so we're going to have m over L. Then the integral of x squared dx is x to the third over 3, evaluated from 0 to L. And we end up with 1/3 ml squared. All right? So here's an example of how to use direct integration to calculate a moment of inertia. I think what I'm going to do here is pause it for a moment, draw in a new coordinate system, and tack a second example on here. Okay, folks, I'm back. I know that was quick. What I did here is I just copied another coordinate system straight down below this. I'm going to call this the prime coordinate system. So instead of x, y, z, this one's going to be x prime, y prime, z prime. So it's just a different coordinate system. I don't really need this original. I can erase it if I want. But what I'm going to do now is try to calculate the moment of inertia of this bar about this z-axis here. So we're going to imagine that this bar can somehow rotate about this axis right here. That is a distance d down from the first coordinate system. So as far as how do we do that, and the answer is exactly the same way. We've got our chunk here. We are going to find its mass the same way, m over L dx. We're going to need the distance from this chunk to the axis of rotation. So I'm going to draw that in here. I'm going to draw that in green here. That's going to be this distance right there. And again, you got to imagine, this rotating like about the z-axis. Now, that distance is not equal to x, right? In this picture, this is x. This is d. The distance we want r is this distance, and I'm going to go ahead and write r squared is going to equal x squared plus d squared from Pythagorean theorem on this triangle. So the moment of inertia of this chunk about this point, right, di, is going to equal m over L dx, there's your mass, times this distance squared. Now I'm going to go ahead and write that as x squared plus d squared. That's equal to, right, this quantity would equal r squared. Our total moment of inertia we're going to get by adding those all up. And I'm going to go ahead and put that dx last. And x again is running from 0 to L. Now, this has two terms to it, so I'm going to go ahead and separate that. So our first integral is going to be m over L, integral 0 to L, x squared dx, plus, now the next integral is going to be m over L, integral 0 to L of d squared dx. And this d is a constant. It can come out in front. I could have just written it out in front there the first time, but I'll go ahead and finish this up here. All right, equals, right, back to this one. M over L, integral x squared dx is x to the third over 3. Evaluated from 0 to L is going to give me L to the third over 3. Plus m over L d squared times the integral of dx, which is x, evaluated 0 to L. So that's going to give me just L. And you'll notice here, let's see, we're going to end up with 1/3 ml squared for the first term, because 3 L's up top, 1 at the bottom, plus here these L's are going to just cancel, and that's just going to give me a plus md squared. So there's an example of how to use direct integration to find the moment of inertia of a mass about, really any axis we want. Now, it turns out there's other ways to deal with moment of inertia. There's what's called the parallel axis theorem, but I think what I'll do is leave, make a completely separate video out of that. So I'm going to call this one done. Have a great day.